Okay, good morning. It's November 4th. I hope you turned your clocks back early Sunday morning because it's fall back, spring ahead in terms of the time change. We gained an hour on Sunday. And this is Monday, and this is the Western Automation 7 a.m. technical class. And I'm going to share the screen. The subject today is Matrix VFD technology. So, please tell me if you cannot see that screen. You should see something that says U1000 industrial matrix drive.
Yes.
Thank you. Okay, some very, very basic stuff, and that would be comparison of topologies. We're going to go over that quickly in this class. The original drive, which is still 90% plus of what's sold today in the variable frequency drive market. Another amazing fact in my career. This was developed in 1983. Well, actually, it was developed in the early 1980s. 1983, Toshiba introduced it to the North American market in the model line VT130G1. Forever impressed upon my mind. Yaskawa came out a year later with the G2 drive, and this replaced the SCR, silicon controlled rectifier, based switching devices of the early variable frequency drives. Early variable frequency drives were very rough on the motor, could not produce more than a 6-to-1 speed range, and had a difficulty doing 6-to-1 constant torque. So for the most part, they were put on fans and pumps, and they were promoted as a great tool for energy savings, as VFDs have always been promoted and still are today, because you now could vary the speed of the fan or the pump to create the flow that you needed and reduce the power of the motor in doing so, reducing power draw. It was touted as a huge energy savings tool. Great technology for the day. Reliance Electric, who was owned by Exxon at the time, came out with a full-page ad in the Wall Street Journal saying that they were going to change the face of energy usage in the United States. And what they meant was they were going to introduce the variable frequency drive. And they wanted to get their stock price up because they thought they had the new golden gun. Well, the SCR drive proved to be extremely rickety and unreliable, especially by today's standards. In my memory, I used to start up 10 and fully expect 3 of them to blow up in my face. Brought enough circuit boards along so I could replace the boards that blew up and get the 10 drives running eventually. And that was the order of the day. It was normal. When this drive came out, we were able to do 6-to-1 constant torque easily. We could do 100-to-1 speed range, and honestly, we were able to do 20-to-1 constant torque. So it was a revolution. Not only that, when you started up 10 typically started up, you didn't blow up 3. We have continued to use this design since then, 1983. The point I'm making is that think about your cell phones, think about your computers. There were no personal computers when this drive came out. A personal computer in the day cost $4,000 in that day's money, and used DOS and had no color. It was black and white. And the dot matrix printers that came along with them, you could barely read them. But we all thought it was great because it was the latest technology. This was the latest technology. It's still around today. We don't use dot matrix printers anymore. We have more power on our cell phones than we had on the best computers that big companies were using in their servers back in 1983. But for some reason, this is stuck around. And it eventually morphed into this, which is the 18 pulse. This block here represents this drive. And all this stuff in front of it, all these blocks here, are filters that are required because this drive is very disruptive to the power line and causes a lot of distortion and reduces your power factor, bad things. It was also extremely abusive to the motor and spawned the whole inverter duty motor industry, where motor manufacturers had to bulk up the motors to withstand the chop-chop waveform of the variable frequency drive. But again, back in the day, it was great. This was really fantastic technology. Not so much today. In order to fix the problems going back to the line, which reduced the power factor, caused a lot of distortion, common mode currents screwing up the ground plane, causing instruments to bounce all over the place, they came up with the active front end, which is nothing more than this section here of the original drive. This is the original drive, flipped around and connected so that it pointed back to the line. Bottom line here is, in this design, you can shape the waveform here as you have to because you're putting a voltage and frequency out to the motor that's different from what you're getting from the line. You get 460, 60 hertz from the line. You want to be able to put out 230 volts, 30 hertz to make this motor go half speed. So this is an active section called the inverter, and you can control it and program it to put the voltage and frequency you want out to the motor. This is a diode bridge. There's no control of the diode bridge. These diodes in the normal variable frequency drive are not connected to the control board. They're just passive devices. They rectify AC to DC. And then the inverter section inverts DC back to AC. So we wanted to replace this static section with an active section so that we could then shape the waveform going back to the drive or to the power line and not distort the power line and not reduce the power factor. A la the active front end drive came out, in the 90s. It's not innovative technology. It's the same technology as 1983, just with a section flipped around and connected. This section here, the original diode bridge, as you can see, is not connected anymore. It's just there for illustrative purposes of this diagram and actually doesn't exist in the active front end drive. You have an inverter section here with its transistors and effective diode bridge. You have transistors and effective diode bridge facing the power line. You can now shape the waveform going back and forth. This is actually a regenerative drive. You can power the motor, passing power from the line to the motor. When the motor regenerates, such as a hoist going down instead of up, the load drives the motor becomes an alternator. That power is rectified through this diode bridge here back to DC on the DC bus, and we now can push that power back to the line. Again, a huge energy savings, right? A hoist, an elevator, an escalator becomes effectively parasitic power consumption. What you lift must go down. What goes up must come down. And when it comes down, you put the power back into the line, less the operating inefficiencies. So very, very important development. However, this is not new technology. This is basically 1983 regurgitated. And then we have matrix drive. And the matrix drive, this is a better diagram of the matrix drive, is basically massively simplistic, a huge change from this. Number of parts, and it's just basic simplicity. Matrix drive is nothing more than 1, 2, 3, 4, 5, 6, 7, 8, 9 two-way switches. There's no DC bus. There are no capacitors associated with the DC bus. There's just a direct switching connection. And if you turn on, let's say we turn on from R, we just turn on this transistor right up here and connect it to U. From S, we turn on this transistor and we connect it to V. And T, we turn on this transistor and we connect it to W. We have basically a 3-pole contactor. This transistor gates on and stays on. It doesn't pulse. The matrix drive can be made into a contactor, directly connecting the motor to the line. Why is that important? Well, it tells you that it really is an AC to AC conversion. Number two, when we're running at full speed, we have this mode in the matrix drive called eco mode, where we do that exactly. We just turn the matrix drive into a contactor. Because why pulse to the motor if you've got 60 hertz, 460 volt power, and you want to go full speed? No, just pass that power just like you did back in the old days with a contactor. Motor's happy as a clam in mud, runs full speed, no harmonic distortion, very good efficiency. So that eco mode is possible because the AC to AC conversion is direct in the matrix drive. It is not through an intervening DC bus with a big capacitor bank. This, in essence, this DC bus here, just ignore that diode bridge. As I said, it goes away. But this is the positive rail. This is the negative rail of the DC bus. That's a gigantic filter between the AC line and the motor. And it has to be because of the technology of the day required it. So, suffice it to say, matrix drive is a significant improvement. And now we're going to get into how to explain this to people, because especially with all the negative propaganda coming out from some of our most respected competitors, you know, when the ABB guy comes in there and puts that white paper down there and starts to say what he has to say, there's a certain percentage of the population is going to believe him. I mean, it's ABB, for crying out loud. This is not a company that's going to go out and tell lies. And that's the general impression. I'll give you an example later on of how that actually has affected things and how I had to counter it. So, matrix technology, direct switching. I welcome you and encourage you to read this white paper to get a much better detailed set of vocabulary to speak in terms of this subject. There you go. There's the 3 technologies: 1983 Toshiba drive, active front end, and matrix technology. I'm going to take one example of what they say and deal with it from a technical standpoint. And when you get this kind of opportunity, it's really great. I was able to do this maybe 6, 7 months ago at several of the water districts. And once you are able to counter the propaganda and show it for what it is, you unmask this disinformation, and people go, "Oh, I get it," and we win customers because matrix drive really does work. The other thing that helps us to win customers is we have installations out there now that are operating for literally years. We've had the product out since 2010. And I'll just cite one example. When we put a matrix drive in and replace older technology, whatever the power factor of that older technology, when we turn the matrix drive on, regardless of load and speed, the power factor on the line for that particular installation is 0.98. Acceptable power factor in a power plant is, depending on the spec, but it's typically above 0.9. We're running 0.98, regardless of load and speed, all the time, 24/7. When we put 3 of these units in, 3 350 horsepower units in to the Whittier Narrows water reclamation plant, which was done well over a decade ago, we replaced 3 18-pulse systems, and the power factor went to 0.98 on that 1,000 horsepower worth of drives, which was a significant portion of the power draw on the plant. Southern California Edison, a couple of weeks later, called the plant manager and said, "We're coming in to do an inspection." They didn't ask, they just said they're coming in. They suspected that this plant, because of the drastic change in the power factor, was cheating and pulling power from somewhere and not paying for it. That's how drastic the effect is when you put matrix drive in versus the old technologies. You immediately elevate the power factor to 0.98. Now, for those of you that don't understand power factor, I will spend a little bit of time explaining that, because that's one of the major benefits of matrix technology. Power factor consists of 2 components: displacement power factor, where the current in time lags the voltage. Here's the voltage starting up on its sine wave. This is single phase. Obviously, most power is 3-phase. And here's the current lagging it. When does that occur? That actually occurs when a motor is connected directly to the line via a contactor. This was a problem back in the old days before VFDs. Lagging current drew down the power factor, and you want your power factor to be above 90% or 0.9. Power factor is a ratio of what the power company gives you versus, well, sorry, wrong slide. No, I don't have it here. Power factor is a ratio between the power that the power company gives you and the power that you actually use to move your load, whether it's water, air, a hoist, what have you. The difference being the power that's wasted. Now, if you use the fluid analogy, if I pump 100 horsepower into a 10-inch pipe, and that pipe is nice and clean and smooth on the inside, and there's nothing in the way, most of that water is going to flow very nicely down to the delivery point. And you will get some waste energy in the friction of the water on the inside diameter of the pipe. And you can calculate that using your Hazen-Williams calculations, and that will come out to, maybe 2-3% of energy that's wasted because of the friction of the water on the inside diameter of the pipe. And the power factor in that particular case would be about 0.97. 97% of the energy being used to move the water to its destination. Put a gate valve in there, or turn 90 degrees, or neck the pipe down, and the power factor goes down because you're wasting more energy going around the 90-degree curve, or the turbulence caused by the gate valve. But in a direct connection, it's very efficient. However, when the electric motor is running at less than full load, that's when the current starts to lag the voltage, causing an inefficiency and reducing the power factor. That occurs because an electric motor, like a car, has an idling current. If you get 30 miles to the gallon out of your car, driving down the road at full speed, and idling, you should be consuming 0. But you're not. The engine's still, believe it or not, consuming, in some engines, 30 to 50% of the fuel just sitting at the stoplight versus going 60 miles an hour down the freeway. That idling energy is wasted. It's lost. That's why a lot of your new cars basically turn the engine off for after 2 seconds and then start up again when you push on the accelerator. That's what causes, that's an analogy to this lagging current. When the motor unloads, the current lags the voltage, and it causes an inefficiency in the power line. So power factor is displacement power factor, and then this distortion power factor, and the two equal total or true power factor. Distortion power factor is what we deal with today, because a VFD has pretty much no displacement power factor. So we can take that off the table. And as I mentioned before, when the matrix drives goes into eco mode and basically acts as a contactor, it only goes into eco mode when the motor's at full speed, full load. Therefore, the displacement power factor is not bad because the current doesn't lag the voltage very much when the motor's going full speed, full load. The distortion power factor is that gate valve that I talked about in the pipe. That gate valve's the VFD, and it causes all kinds of distortion. And so much so that we can significantly reduce the power factor. To give you an idea of how much distortion is actually caused by the VFD, let's see if we can pull up a good diagram on that. There it is. Here's your distortion. We want the current distortion to be less than 5% so that the power factor can be up around 0.97, 0.98. This is just the standard VFD with the diode front end. And look at the amount of current distortion from those diodes. And the true power factor drops to 0.75, which is completely unacceptable. This is a VFD with a little filter in front of it. This happens to be a VFD with a 12 pulse or 18 pulse. In this case, at 6%, it would be 18 pulse. At 12%, it would be 12 pulse. And here you're starting to get into the range where the waveform looks kind of sinusoidal. It's not so distorted. And you get your power factor up to where you need it to be. But only at full speed, full load. This passive filter technology, as I said earlier, doesn't work as you vary the speed. Now, here is your AC to AC, and I'm going to include both active front end, AFE drives, and matrix, which is a special case of active front end in this category. And here, you're less than 3 to 5%, but the important thing that this chart doesn't show is that this is active. As you go up and down the speed range, this stays at 3 to 5%. These technologies do not. This is only their best, which is at full load. And here's your power factor, 0.98. And as I've said, every time we put a matrix drive in, we go from this, or this to 0.98. And it stays at 0.98 no matter where they run the load and at what speed. Case in point, City of Lakewood, they have this beautiful SCADA system running their pumps. The City of Lakewood is a freshwater utility, supplies water to the people in the City of Lakewood. SCADA stands for Statistical Control and Data Acquisition. Their SCADA system reports everything back to screens that you can see in the main office. And when you look at the power monitors on the pumps that are running on matrix drive, they're all pegged at 0.98, regardless of what speed they're running at. You look at the older drives that they have in the plant, and they're running 0.75, I saw one at 0.67. So the change is huge when you go to matrix technology or active front end technology, as we proved at Whittier Narrows, the story I told you earlier. So this is distortion. So going back to the other presentation to explain power factor, displacement and distortion equal true. If you want your true power factor to be 0.98, you can't have this, which is not a problem with variable frequency drives, and you better fix this. And that's what active front end and matrix technology does. That's why people are using it today. Because the power company is sick and tired of people abusing the power factor and running true power factors in their plants at less than 0.9, 0.85, which is very common. And the grid can't stand it anymore. because the grid's already overloaded. How do we fix the grid short term? We improve the efficiency of the power delivery. Therefore, we have to deliver less power to do the same work, to cool the same building, to run the same industrial plant. That becomes on the end user. The end user has to fix that problem. The power company is going to motivate them to do so with money. They're going to say, if you don't fix your power factor, your power rate goes from 12 cents a kilowatt hour to 22 cents a kilowatt hour. So that differentiated rate structure is going to cause people to say, whoa, I don't want to give the power company that money, so I'm going to invest in new equipment. And that's the way the process should work, and in this case it is. Matrix drive, by the way, we can't make them fast enough. We also make an active front-end drive just like everybody else does. That's selling well, but frankly, not as well as our Matrix drives. And from what I understand, Siemens, ABB, Allen Bradley, the rest of the group, they're all having problems keeping up with their active front-end sales. So let's go back to the subject at hand. How do we explain Matrix drive to people? Because it's such a dramatic change, and it's such a great fix for the problem that a lot of people get skeptical. You know, somebody comes and knocks on your door and says, I'm going to put solar on your house. You don't have to pay any money at all, and you'll never pay an electric bill again. And you're going to think, what's wrong with this picture? And actually, if you do it right, solar does result in that. But there's a lot of chicanery out in the marketplace, and the solar industry is getting a bad name because people are coming out making claims they shouldn't make. So people are naturally skeptical. And when we come to the market and we say, we've got the perfect electric valve, we're going to fix your problems on the power line side, and you won't have to pay more money for your power, and we're going to treat your motor better. The fact is, on a Matrix drive, you don't really need inverter duty motors because the output of the Matrix drive is sine wave. People are going to look at us and say, yeah, right, you're a salesman, and how can you tell that when a salesman is lying? Well, his lips are moving. So, how do we explain the Matrix drive properly? And how do we make sure that that gets across? Well, you explain the Matrix drive properly by reading that white paper I just showed you, by going to this class, by reviewing these PowerPoints, which I'm going to send you at the end of this class, and educating yourself to speak intelligently about the subject, a very important subject. How do you get the person to understand what you're saying? Well, at the beginning of this class, I referred to that. That's a whole different can of applesauce. And that's psychology, and I'm an electrical engineer, so I can't say I know much about that. But I'm going to use an example. Here is a letter that I'm going to, let's see, I have to look it up. Bear with me. Okay, so we submitted a document to LA County Sanitation, as I said, which was a rewrite edit of their main specification. And here we have a letter that came back from Xylem, one of their major pump manufacturers. And this is part of the disinformation, unintended, I'm sure. Maybe I should edit this guy's name out of here, probably should, but sorry. Basically, this is their requirement for using low voltage VFDs on their pumps. The following is a summary of minimum requirements for a low voltage VFD, implying used on our Xylem pumps. Variable torque pulse width modulated drives are to be used. That's the standard 1983 technology. drive should have an output kVA rating that is 10% higher than the input kVA of the motor. That's good service factor. I would always oversize the drive a little bit for the motor. Why? Well, the motor will be rewound 2 to 3 times during the lifetime of the drive. Each time the motor is rewound, it loses a bit of its efficiency no matter how good the rewind is. And that loss of efficiency is about 2 to 3%. So by the time you get to the third rewind, you're at 10%, and you don't want your drive to be undersized during the lifetime of the motor. So just for that reason alone, and there are other ones, this is a good reason to have this service factor of the VFD on the motor. I'm going to skip this and come back to it. The VFD shall have the capability to have its carrier frequency adjusted in the 3 to 4 kilohertz range. That's the switching frequency of the pulse width modulated waveform, and for a lot of reasons, that's a good idea. It reduces the amount of switching stress on the transistors in the VFD and allows the VFD to last longer. However, at 3 to 4 kilohertz, 2 to 4,000 times a second, that's right in the audible range of the human ear, and it sounds like which will drive you freaking nuts if you're standing next to the motor. So you have to account for that too. But it does reduce the long-term stress to the motor insulation, because at 3 to 4,000 times a second, you're hitting the motor insulation with about 3 or 4,000 voltage spikes a second. If you bring that up to 10 or 12 kilohertz, 10 or 12,000 times a second, now you're hitting it with 3 times the number of voltage spikes. Because every time you pulse the transistor on a PWM-based drive, we'll talk about this in a second, you have a voltage spike hitting it. So at 3 to 4 kilohertz, you're reducing the voltage spikes and the deterioration of the motor winding. You're tripling the life of the motor, basically, in that regard. Okay, here you've all heard that distance of the motor leads from the VFD can be a problem because of these voltage spikes. dVdt is a fancy mathematical way of saying voltage spike. It says change in voltage over change in time. And it's a large change in voltage over a small change in time that defines what a voltage spike is. At 130 feet or more, these voltage spikes, they amplify, they grow. And at 1,000 feet, your voltage spikes can be 3 to 4 times what they are at 100 feet in terms of amplitude, severely damaging the motor insulation. So everybody says, hey, you know, once you get beyond 130 feet, we need to put some filters out there. dVdt, or voltage spike filters. Matrix doesn't require this. We'll go into that in a second. So back to this. And this is from a major manufacturer to their major customer. This is an example of what we have to combat in order to get truth out there, because selling matrix drives means truth wins. You put the truth out there in the customer's mind, you're going to win, because it is truly a better technology. 6, 12, or 18 pulse designs are acceptable. That's the old style. However, both 6 and 12 pulse drives will need to be provided with proper harmonic filters to reduce the harmonic content such that the total voltage harmonic distortion delivered to our motor does not exceed 5%. An acceptable alternate solution is to supply active front-end circuitry in the drive. He's talking about 6, 12, or 18 pulse or active front-end drives and the effect that they have on the electric motor. He's not talking about the power line. So with that in mind, let's go back to this. How can that be when in comparing the topologies of the drive, there's your variable frequency drive. Remember, this variable frequency drive with all the filters up front here, 6, 12, 18 pulse, is the same output to the motor. The filters go here, right? He says that with 6, 12, or 18 pulse, you got to put filters here to protect the motor, but that you don't have to do it with an active front end drive. This is an active front end drive. It's the exact same circuitry going to the motor. So why, in this case, do you need filters when, in this case, with the same circuitry, you don't need filters? Obviously, that's technically not correct. This is an example at a highest level of communication in corporate marketing where disinformation is being put into the marketplace, causing people to do wrong things. Why? Going back to this, anything happening here on the line in terms of power factor, distortion, is not seen by the motor. Why? Because you have a DC bus heavily filtered with big capacitors that basically puts an electric barrier right here between the input and the output. The motor doesn't see what's going on the line. Period. That's the fact. You go to the active front end, exact same thing. Same motor circuit technology. Yeah, we got an active front end up here, but that's affecting the power line. Right here, we have the DC bus. And again, with the huge capacitive filters, that's the representative symbol for capacitance. This is an electrical barrier between the input and the power line and the output and the motor. So the statement is just patently wrong. And it's a good example of what we need to communicate to the customer base on and counter, because we are trying to put truth out there. That's why I only ever speak in technical terms. Never, ever bash the competitor, because that just lowers you down to the level of a competitor that's putting out disinformation. And we go for educating the customer with technical reality. My response to LA County basically said exactly that. Now, let's take another piece of disinformation on the Matrix drive. And that is that the Matrix drive has poor output voltage and as such damages the motor. Okay. Here's the ABB white paper. Let's see. Marketing of matrix converters may not tell the whole story. Be skeptical of marketing documents supporting matrix converters. Marketing documentation may advertise best features, yet fail to disclose matrix converter cannot achieve all these features at once. And they specifically refer to they refer to the fact, I'm sorry, I should have prepared myself better on this document. They refer to the fact that the matrix converter has an excessive voltage drop that the active front-end technology does not have. Let's see. Here, from performance perspective, removing the DC bus capacitors creates a significant output voltage, harmonic mitigation, power factor, and power loss ride-through limitations within the drive. As an example, DC bus capacitors, capacitorless AFE drive matrix may only produce 92% or less output voltage when it operates in its low harmonic mode. They're claiming that the matrix drive undervoltages the motor and reduces the motor life and performance. Now, that is a pretty good scare tactic, and it's a general statement. And if you read through this document, they really don't put numbers behind that claim. So I'm going to try to put some numbers behind that claim. Here is what we actually look at in terms of voltage drop on the matrix drive. And by the way, they are correct. In this active front end scheme, you've got capacitors here on a constant voltage DC bus. And the matrix drive doesn't have capacitors and doesn't have a DC bus. So their claim is that because we've got this capacitance-backed DC bus, capacitors are like batteries, that we can maintain full voltage to the motor under more conditions than the matrix drive can. Fact, the capacity of these capacitors to supply a motor with energy when the power line is cut off is about 1 millisecond before the capacitors drain out. They're not gigantic batteries. These capacitors are not there to act as batteries to back up the motor when there's a power line dip or power line outage. They're not a UPS system. These capacitors are here as filter capacitors to smooth out the DC bus. They're sized to take out the ripple, which is plus or minus 20 volts on the DC bus once we go through the rectifier. So saying that they're here as a giant UPS battery bank to back up the motor is just patently false. And you can prove that by just noting the capacity of these capacitors. Again, this is a 100 horsepower motor, it's 75,000 watts, right? It's 750 watts to the horsepower. So at 75,000 watts, these capacitors get drained out in a millisecond. Not much backup. That's one fact. The other fact is this. Output voltage. This is a typical output voltage curve of a VFD, 230 and 460. Let's just talk about the 460 volt application. And at 30 hertz, we're at half voltage. At 60 hertz, we're at full voltage. That's what the motor likes to see. NEMA says that a motor must be rated to operate at its output rated torque with a plus or minus 10% voltage variance. Now, 10% reduction on 460 is 414 volts, which is less than the voltage drop across the matrix drive. But we'll use 10% just to be conservative. If the voltage drop across the matrix drive with a 460 volt input is 10%, then we're going to put a maximum of 414 volts into that motor. From 0 to 54 hertz, we're fine, because we have enough voltage to satisfy this voltage requirement on this volts-hertz curve for the variable frequency output. Above 54 hertz, ABB is correct. If the matrix drive voltage drop is 10%, which it's not, it's less. However, I said we're going to use 10%. So above 54 hertz, we start to undervoltage the motor a little bit because of the voltage drop of the matrix drive. However, we never get less than 414 volts. Therefore, we are within the NEMA variance, even if the voltage drop across the matrix drive is 10%. Now, most power in the United States is 480 volts versus 460 volts, so that helps us a little bit. And the matrix drive voltage drop is not 10%. But if we compared this to the other topologies, we have to ask ourselves, what's the voltage drop across this drive? It's not zero. And look at the number of components we're going through, and look at the number of components we're going through with matrix technology. Is there no voltage drop across this product, which we've been using since 1983? Of course there is. And it's actually very similar to the voltage drop across the matrix drive. Even if you have a fully capacitance backed up DC bus, you still have to go through these transistors to get to the motor, and there's voltage drop across those transistors. So as the guy in the Chicago radio show, Paul Harvey, used to say, and now you know a little bit about the rest of the story. If they just say one thing, oh, the voltage drop across the matrix drive is 10% and it's going to undervoltage the motor. But they don't tell you that, well, we've been doing the same thing with variable frequency drives since 1983. And because of the fact that NEMA says the motor can run at 90% of its rated voltage and still achieve output torque with the correct thermal losses, because that's what the motor is designed for. So that is the counter to the big claim against matrix drive. When you go into more of the detail, which we don't have time to do today, you will find that from an electrical engineering standpoint, the voltage drop of the matrix drive is just pretty much the same. It's within 2 or 3% of the voltage drop of the drives we've been using for the last 40 years. Therefore, the claim's really not that fair. One defense of ABB, in their technology, again, just eliminate this diode bridge, it's not here. In active front-end technology, whether it's ABB's drive or whether it's Yaskawa's active front-end or Siemens or Allen Bradley, whoever, the reality of it is that you can, if you put some extra circuitry in here, you can boost up the DC bus. Actually, I take that back. You don't need extra circuitry. You just use these transistors. And there's an inductor here, so that's the only added circuitry. But the fact is that if you pulse into that inductor, you can boost the voltage on the DC bus. And from an active front-end standpoint, they have to do that. We have to do that in our active front-end drive. Because if I don't have a higher effective voltage here than the line, current will only pass from the left to the right. And then I cannot use the transistors to shape the waveform that I'm drawing from the line, and therefore reduce the harmonic distortion, and therefore maintain the power factor. This design, active front end, you have to boost the voltage on the DC bus for the reasons of input section power factor performance. ABB says, oh, no, we're doing that also so that we can boost the voltage to the motor. I'm going to ask you to stay with me for another 7 minutes because I need to explain the last item on this presentation. The fact is that boosting the voltage on an active front end is necessary to maintain power factor performance. It's not designed in to boost voltage to the motor. Again, the bottom line is that we've been fine with the voltage drop of the variable frequency drive ever since the days of Toshiba in 1983. Now, the last subject I want to talk about, which is a significant advantage to Matrix over what they call traditional VFDs. Another way of talking about it is a DC bus-based pulse width modulated output VFD. Because let me see if I can show you a picture of pulse width modulation. That's not it. Hang on. There we go. This is pulse width modulated output of a VFD, whether it's a diode front end VFD, whether it's an active front end VFD, but it's not matrix. Pulse width modulation means I can vary the pulse width. Notice that this one's wider than this one. They get narrower and narrower. They start to grow again. Depending on where we are in the sine wave that we are trying to simulate, red being the perfect or reference or target, we're using voltage pulse width modulation to create an analog current sine wave to the motor. We want red. What we actually get is blue, because every time we pulse on, the current obviously goes up in the motor. When we pulse off, the current starts to drop, coincident with this gap, this off time. And then we pulse on again, and we climb further up the sine wave. So as you're climbing the sine wave, you widen your pulses. When you want to slow down and start going down again, you use narrower pulses. And then when you start to go up again, the pulses start to widen. Pulse width modulation technology used to simulate the analog sine wave. We can only pulse width modulate on the traditional VFDs. We can't pulse amplitude modulate. It'd be nice to, because when we're trying to simulate the lower portion of the sine wave, we would like to use a half height or quarter height pulse, but you can't on a constant voltage drive. That's just the nature of it. It's what we lived with since 1983, pulse width modulation. There you have it. The problem with pulse width modulation is that every time you turn the transistor on, this pulse here, what's not shown is the voltage spike associated with turning the drive on. You go and then come back down again. That voltage spike, the dVdt, change in voltage and change in time, is what harms the motor insulation. It's what you put filters on the output for, to protect the motor. Longer motor lead lengths, the higher the voltage spike on every one of these pulses, every time you turn on. That is one of the downsides of using a constant voltage DC bus based variable frequency drive, what I refer to as the traditional variable frequency drives. What's the difference with matrix drive? How does matrix drive deal with this? Matrix drive has pulse width modulation also, but it also has pulse amplitude modulation, something traditional VFDs don't have. It's a watershed. It's a huge gain in performance for the matrix drive and allows us to significantly reduce the dVdt. So, what does our output pulse look like? The matrix drive, as I said, we switch directly from the AC line to the motor. Here's the AC line, three-phase power, green, blue, red. At any instant in time, I can choose from 3 different voltage levels. And in this enlargement here, I have VR to VS, VS to VT, and VR to VT, 3 different amplitudes. So in addition to pulse width modulation, I have 3-level pulse amplitude modulation available to me. And therefore, we never full height switch to pulse because we want to avoid that dVdt. So our pulse looks like, here's 0. We take the first step up. We take the second step up, which is the full height. Then we step down again, and then we step back to 0. This is one output voltage pulse of a matrix drive. Instead of the full height pulse with its attendant full height spike, we step up. And we reduce the dVdt significantly, which is why matrix drive claims We don't need output filters on long motor lead lengths. Our DVDT is much less. It's what we claim. Now, it's also why our output waveform, if you remember the pulse width modulated waveform that I showed you, it's basically all pulse heights exactly the same. Therefore, all DVDT is constantly high throughout this phase of the sine wave. If you look in detail, and this is not a very good illustration of it, but if I blow it up, maybe it'll look better. You can see that we have a kind of a varying pulse height and less DVDT. If you blow up one of our pulses, here's that 3-stage amplitude. This is an actual oscilloscope reading. So this is a different time base. Each one of these lines here is one of these. This is just blown up. First level, second level, third level, back down again. First level, second level, third level, back down again. Because again, we can get 3 levels of voltage at any instant in time off the 3-phase line. We switch it directly to the motor lead that we want. Motor winding 1, motor winding 2, motor winding 3. And our pulse is not full height. It's pulse amplitude modulated as well. Pulse amplitude modulation plus pulse width modulation means better switching to the motor from the matrix drive, better simulation of the analog function, less DVDT. And it's 8:09. I know I've covered a lot of ground here. Are there any questions? I'm going to stop sharing the screen. You can see my ugly mug. Please, if you have any questions, if not, yes, please.
Yeah, I was going to ask you, was going back to the eco mode where you talk about how the VFD switches on to just allow the pass through to the motor. How does it still correct displacement if it's just passing through? Because wouldn't that just be a
great question? Because we only go to eco mode at full speed, full voltage, and actually the eco mode can switch on. You can program this in the drive. You can switch it on at, say, 57 hertz, and then it seamlessly goes into eco mode and comes back out of eco mode as the demand requires the motor to speed up and speed down to maintain pressure or flow or whatever it is you're trying to maintain. That seamless transition back and forth is not, it's a natural feature of the matrix drive. So when we transition into eco mode, we just gate the transistors on. At that point, Wyatt, we're at full speed, full load. The displacement power factor of an AC motor at full speed, full load is acceptable. It's only when the motor unloads, and in a fan or a pump, you've got to reduce the speed. To unload the motor. Do you understand?
Yeah, because there's a mention of when you have all the motors on a contact, how you'll get, bad, like maybe around 0.85 or whatever it is. So I was curious, since it's just switching on, it's no longer able to correct that displacement factor, but it's still, I understand.
We will not switch to eco mode, even though we can only switch to eco mode at 60 hertz, right? So full speed.
Yeah.
But you don't have to switch to eco mode. So if the motor's not fully loaded at full speed, then don't switch to eco mode.
I see. Okay, cool. Thank you.
When we do switch to eco mode, in summary, the motor's at full speed, full load, and therefore its displacement power factor is quite acceptable. Any other questions before we sign off today? Thank you, by the way, for staying the extra minutes. I hope it's a tough subject to cover in an hour, and I'll probably try to do an enhancement of this in the near future. By the way, next week's class is canceled because our president is calling a meeting off-site for everybody at Western Automation. So nobody will be available to do the class, and we will pick it up the week after. And then we're off for Thanksgiving again. So we're kind of every other week until after Thanksgiving. I'll send an email out. If any of you have any questions on this, please send me an email. I will be glad to respond in detail. I'm sure it's not a question I haven't had before, although I welcome new questions because they're new challenges. In the meantime, it's 8:13. I've taken more than enough of your time today. Time to go to work, and I wish you a great week, and we'll see you in 2 weeks for the next class.
Thanks, Pierce.
Have a great time.
Thanks, Pierce.
Thank you.
Thank you, Pierce.
Thank you, Pierce.
Bye.